Welcome everyone from Lecture Theatre 1 in the School of Chemistry at the University of Bristol, and obviously these are strange times, but we are here and we're going to be going through a lecture called A Pollutants Tale, and this is the climate special edition that we're going to give you. I'm Dudley Schauerkross. I'm a Professor of Atmospheric Chemistry in the School of Chemistry at the University of Bristol, and this, I can't help saying this handsome man here is Mr. Tim Harrison, who is the Director of Outreach, Science Communicator in Residence, and numerous other titles which he's told me not to tell you. And he will be doing all the demonstrations, and I'll be talking through some PowerPoint slides. But let's make a start. And the first thing that we want to think about, to put everything in context, is the composition of the planets in our solar system. Now, obviously quite a lot has changed in terms of our understanding of the solar system in recent times, but their composition hasn't, and our understanding of that hasn't. And so we have the giant gas planets, the Jovian systems as they're called, Jupiter, Saturn, Uranus and Neptune, and they vary in the composition, but the bulk constituents are the same. They're mainly hydrogen, H2, with some helium, He, and the other gas of note in their atmosphere is methane, CH4. And before we go any further and even thinking about these things, I usually ask Mr. Harrison, or Mr. Tim as I call him, just to tell us a little bit about hydrogen and helium, because some people don't know.
Okay, so in these balloons behind me we have some low density gas. Hydrogen and helium are the two lowest density gases in the universe. In fact, these gases between them make up most of the visible universe. They're low density because if we cut the string, the balloons would simply float upwards. What we have in the balloon to my left here, this nice purpley coloured balloon, is helium gas, and the one on the right is hydrogen gas. And both these gases have different chemical properties, which we're going to show you very simply by trying to set the gases alight. So we'll start with the one on my left. We'll start with some helium gas. Helium gas, of course, is in balloons in parties that most of you will have had at some point in your lives. You know it's a relatively safe gas. It's not a particularly poisonous gas. So if we try setting that alight, this is what happens. Not a great deal, just simply a percussive explosion. The gas comes out at speed from high pressure to low pressure. No flame, no chemistry. Full outer shell of electrons. Hydrogen, on the other hand, is somewhat different. Hydrogen will burn in oxygen. Dudley.
Well, thanks for that, Tim. So if we look at the planets either side of the Earth, Venus, which is obviously closer to the Sun, and Mars, which is further away, even though Venus has a very thick atmosphere and Mars a very thin one, their compositions are surprisingly similar. They're mainly carbon dioxide, 95-96% CO2. Nitrogen is the next most abundant gas. And then Venus is slightly more acidic, so there's some SO2 there, which is the next most abundant. And for Mars, it is argon. And you said you didn't need to listen to this lecture to know that the Earth sticks out like a sore thumb. It's not like the giant gas planets. It's not hydrogen, helium and methane. And it's certainly not like our nearest neighbours dominated by CO2. The Earth consists of, as we know, nitrogen is the main constituent, oxygen is a significant amount, and the next most abundant gas is argon. And if you add those three constituents up, you get very, very close to 100%. And so the rest of the atmosphere, or the rest of the constituents, are known as trace gases or trace constituents. And they're in tiny, tiny quantities. So let's start our exploration and think about nitrogen, which is the most abundant gas in the atmosphere. Well, you might not know a lot about nitrogen, but the molecular nitrogen N2 is held together by a very, very strong triple bond, very hard to break apart. And so the bulk constituent, 78% of our atmosphere, is inert. And at room temperature, it's a gas, and is really quite boring. Actually, there's lots of reasons why nitrogen is very important in the Earth system, but we're not going to talk about that today. If you cool nitrogen down to minus 196 degrees centigrade, then you turn it into a liquid, and then it gets a little bit more interesting.
Before we look at liquid nitrogen, we'll just show you one use of an inert gas like nitrogen, in fact of nitrogen. We've got here some expanded polystyrene. So that's polystyrene foam. It contains the polymer polystyrene, and it also contains a lot of unreactive gas, a lot of nitrogen gas. If I take a bit of solvent, the active ingredient in nail varnish remover, universities and industry still refer to this by its traditional name of acetone, but of course in schools it's correctly called propanone. And I take a piece of polystyrene foam and put it into the beaker. And we'll do it if we actually got the right size. Let's see what happens. Of course, I'm not melting the polystyrene foam, nor am I dissolving it. All we're actually doing is disrupting the structure to release the gas that's in there. There's not a great deal of polystyrene in polystyrene foam, and for those of you like a quantitative understanding of how much, let's take a litre of polystyrene pieces, unusually coloured green, but there's a litre of them. We'll use the same propanone and pour that in there. You can see there is very little polystyrene in polystyrene foam. Most of it is unreactive gas. As Dudley suggested, we'll have a look at some liquid nitrogen. Handling liquid nitrogen requires a few precautions. One of the things that we need to use is a piece of glassware called a Dewa Flask, invented by a Scotsman. 2 layers of glass between thumb and finger here. Used to be air between the two. Air gets sucked out, sealed off. So there's a vacuum between the inside and out. These, of course, commercially usually have silver between the 2 layers, and then they get called thermos flasks, which happens to be a trademark. If we added silver here, you wouldn't be able to see the liquid nitrogen. Here is my larger source of liquid nitrogen, another Dewa flask, this time a metal one. Let's see the material. So there we have liquid nitrogen in the act of boiling. Now let's just consider boiling for a moment. The glassware was at room temperature. Room temperature is 220 degrees above the boiling point of liquid nitrogen. Liquid nitrogen boils at -196 degrees centigrade. So all we're seeing here is that the nitrogen in the liquid state is taking the energy, the heat energy from the inside piece of glass of the Dewa, and is using it to overcome the weak intermolecular bonds that holds the nitrogen molecules together in the liquid state. And depending on who's teaching you this, we either call those van der Waals bonds, instantaneous dipole-dipole interactions, or London forces. All the same thing. What you might notice, there's some white stuff coming off the top. Of course, that's not nitrogen gas. Nitrogen gas, if it were white, we would have noticed. What we're getting here is an interaction between cold nitrogen gas coming out and water vapor in the air. The nitrogen gas is cooling down the water vapor and condensing it into billions of droplets of liquid water. So we're actually getting cloud formation. Clouds a little later on in the talk. Water vapor normally at room temperature or at body temperature, you can't see. If you cool it down, you can see. While this is still here, let's do some simple experiments, just some quick ones. Piece of rubber tubing, room temperature. So bizarrely, it's 220 degrees centigrade hotter than the liquid. If you put the end in, you can cause the nitrogen to boil, and out will come nitrogen as nitrogen rain. The reason for that, of course, is as the energy from the warm end of the tubing has been given away to the liquid boils and in turn shoots out any unsuspecting droplets of liquid that are in the way. This is now dangerously cold. It's the same temperature as the liquid. And if you were stupid enough to hold on to that with your hands for 5 seconds, you'd freeze your skin to it, pull your hands away, bits of your dead flesh are left on the pipework, and you get a cold temperature burn. Cold dangers are called cryohazards. Why am I not wearing gloves? Stretchy rubber glove there, latex rubber in this particular case. Your school labs, you might be using the blue version, which is nitrile rubber. However, this happens to be latex rubber. Let's put one in liquid nitrogen, Please notice my fingers aren't in the liquid. If they were, I'd actually get extreme frostbite. And also after 5 seconds, my flesh would have frozen through to the bone. The cytoplasm in each of the cells in my flesh would have actually frozen. I could have then snapped my fingers off. Why no gloves at this temperature? Far too brittle. What we have here is a useless material at cold temperatures. If we need to actually handle cold temperatures for any length of time, we have specially insulated gloves. We'll look at 2 more experiments with liquid nitrogen. We'll look at well, let's do an experiment. There is a balloon full of air. We've actually pumped it up with an air pump so that the constituents in there are the same as the air outside. I didn't actually blow into it, otherwise the gas in the balloon would be slightly different from normal atmosphere, being greater in carbon dioxide and lesser in oxygen. However, what will happen to the size of the balloon if you cool it down? So we've got a fixed volume inside of there. We have a fixed number of particles. Let's cool it down. Is it going to get bigger, is it going to get smaller, or is it going to stay the same size? Well, obviously from your observations you can see it's getting smaller. Let's warm it back up in the nice warm air of the lecture theatre here. We have a reversible situation, a piece of reversible physics here. Those of you that understand the gas laws will know the significance of this experiment. For those of you that don't, think about this. Are the particles, these atoms and molecules in the air, when they're cold, do they actually shrink? And when they warm up, do they get bigger? Or is it just the case that when you cool down a fixed volume of air, a fixed volume of gas, do the particles simply get closer together? And when you warm them up, do they simply move further apart? So is it size or is it distance? Let's find out. 2 pieces of glassware here, sidearm conical flasks. There is a spout here to which we've tethered some balloons. Let's imagine we could put 35 cubic centimetres of liquid nitrogen in there. 35 cubic centimetres of this particular liquid is 28 grams worth. 28 grams of N2, in other words a mole containing the Avogadro number of particles, 6 times 10 to the 23. Let's seal up a system, which is always a dangerous thing to do when you seal up a system producing a gas. A gas, of course, because the glass is at room temperature, the liquid therefore is taking the energy away. And the gas particles are filling up the balloon at pressure until the balloon can't take it anymore, and yet the particles are still, or the gas particles are still spewing out of the side arm. Just think about this for a moment. It's a law in chemistry that says that a mole of gas, a mole of any gas at room temperature and pressure occupies a space of 24,000 cubic centimetres or 24 cubic decimeters. A mole of liquid nitrogen, 35 cubic centimetres. A mole of nitrogen gas, 24,000 cubic centimetres. There is a hell of a lot of empty space in a gas compared with a liquid. Your simple kinetic theory would have told you that. Dudley.
Thank you. So we can think about how nitrogen appears in our atmosphere or why it's there. There is certainly, as you'll see from the figure, this is an electron microscope, a high resolution image of some bacteria chomping its way through some organic material. And what it's doing is breaking down that organic material, which does contain some nitrogen from the proteins that are there, and releases that nitrogen into the atmosphere as N2, but also nitrous oxide, N2O. And there's also some inorganic chemistry going on in the Earth's crust that also produces nitrogen. And because it's inert, its concentration is built up over time, and it's now 78% of the atmosphere. So let's think about the next most abundant gas in our atmosphere on planet Earth, which is of course oxygen. 21% of the atmosphere is oxygen approximately, and it is a gas at room temperature, and if you cool it down to minus 183 you turn it into a liquid. Now Tim's not allowed to do that in this lecture theatre and under these conditions, But if we think about how we end up with oxygen in our atmosphere, it's an amazing process that leads to that, something called photosynthesis. And you have the equation there where you take 6 molecules of CO2, 6 molecules of water, add some energy from the sun, and it turns itself into sugars. Obviously, you have examples of those sugars: bananas, banana plants, apples, etc. are all examples of that. And the waste product is oxygen. It's an absolutely amazing experiment. Now, I usually challenge Tim at this point in the lecture to whether he can make oxygen for us.
I can make some oxygen, but simply not the way plants do. That photosynthesis equation, of course, is the net result of a complex cascade of chemical reactions. And please note that the plants don't, if plants could want, and you do need a brain to be able to want, if plants could want to make, don't want to make oxygen, they want to make sugar. They want to trap the energy from the sun in a chemical format. I can't do that, but I am going to make some oxygen in a far simpler way using the stuff I have in this very fresh bottle. This chemical looks a little bit like water. In fact, it's chemically related to water. Water, as we know, is H2O. This is what you get if you chemically add an extra oxygen to water. You get H2O2, or hydrogen peroxide solution, linking HOOH by single covalent bonds. And hydrogen peroxide, we got the equation up for that one? Yes, we have at the bottom of the slide. Hydrogen peroxide wants to split up, decompose, dissociate into oxygen and water. Now, I've put some food colouring in there to make it easier, hopefully, to see that there aren't vast quantities of oxygen bubbling away from this very fresh solution. Maybe you want me to trap any oxygen produced using some best washing up liquid. Give that a bit of a swirl to make it homogeneous. Washing up liquid has a tendency to float on top of hydrogen peroxide solution. Not a great deal of evidence of any oxygen production, but let's cause it to happen faster. Let's cause that dissociation faster. The equation tells you if you start with peroxide, you should end up with water and oxygen. It doesn't tell you how fast it's going to go. The reaction that we have here is obviously a slow one. We'd have to wait the rest of the day to see some bubbles of oxygen gas fill up the tube. I'm going to apply some simple GCSE chemistry here and use a catalyst. The catalyst I have here is the iodide ion attached to a spectator ion of potassium. And if we add this in, we should see a catalytic decomposition of hydrogen peroxide. And there we have a large amount of oxygen gas being trapped into some washing up liquid and about to collapse over my beautiful tablecloth. You might want to stick your fingers in such a thing. I don't recommend it. This is a highly exothermic reaction, and being exothermic, it means an awful lot of heat's given out. The foam is probably hotter than boiling water. The white stuff coming off the top, let me remind you, can't possibly be steam, because you can see white stuff. Steam is colourless. What we're getting off here is condensed water vapour that originated as steam. I'll move this one out of the way. And over to you, Dudley.
Thank you, Tim. So now we've thought about the two main gases in our atmosphere, we want to think about the atmosphere itself. And our atmosphere is highly structured. And the first region of the atmosphere we're going to think about is called the ozone layer, or the stratosphere, which extends from about 10 kilometers in altitude up to about 50 kilometers in altitude. And the other thing that's interesting about this region is if we look at the altitude temperature profile of the atmosphere, we find that going away from the surface and going up into the atmosphere, the temperature drops up to about 10 kilometers, and then it starts to rise again in this region known as the stratosphere, where the ozone layer resides. And then when it gets to the top of the stratosphere at about 50 kilometers, the temperature drops again, and this is a region known as the mesosphere, and that extends up to about 80-90 kilometers, and then it starts to rise again in a region known as the thermosphere. But we're going to think about the stratosphere for a moment. And the stratosphere is a really, really important part of our atmosphere. I'm sure you know that both oxygen, O2, and ozone, O3, that is formed in the stratosphere, protect us from harmful UV radiation. So they absorb this radiation from the sun and stop it from getting down to the surface, where it would cause significant problems to organisms such as ourselves. And it's a rather simple process. The oxygen, O2, absorbs a photon of light in the UV and gets broken apart into two oxygen atoms. Those oxygen atoms can add to an O2 molecule to form O3, to form ozone. And the ozone itself can absorb a UV photon, slightly less energy than the one that O2 absorbs. And it then breaks apart to give us back O2 and O. It's an amazing cycle. It's called the Chapman cycle. Not surprisingly named after Sidney Chapman, who proposed it. And it allows the ozone layer to form, but it also protects us from harmful UV radiation. And so we can think about what has happened over recent times. We're not going to go into the whole ozone's whole story, but back in 1985, Joe Farman from the British Antarctic Survey and colleagues alerted us to the fact that there was a problem with the ozone layer over the Antarctic, and that ozone was being depleted. And as a result of that, a number of protocols and amendments have been put in place which have stopped the production of the chlorofluorocarbons, the CFCs, and introduced replacement compounds, the HCFCs, the hydrochlorofluorocarbons, and HFCs, the hydrofluorocarbons, which have less impact on the ozone layer. And so it is predicted now that the ozone layer will be a thing of the past in around 2050. Sorry, the ozone hole will be a thing of the past in around 2050, which is a very good thing. And if we look at some recent data, we hopefully can convince ourselves that this is actually going to be the case. So if we look at the area of the ozone hole over the South Pole, we see that it was increasing over time, and it's been flattening off in recent time. And even though the data are quite scattered, we can convince ourselves that it is starting to decrease. And the minimum amount of ozone observed over the South Pole has also dropped, leveled off, and we believe that it's starting to recover. And so the minimum ozone hole, we've reached the lowest level, and it's starting to get better. And the other thing, another piece of evidence we can bring to bear is that I work with in a group that is part of a worldwide program of measuring the levels of CFCs and other ozone depleting substances. And again, you can see from these figures that two of the most important ones, their concentrations were rising over time and now are dropping. So we're confident that the ozone hole will be a thing of the past, and that the stratosphere will heal itself. Okay, well, let's now focus for the rest of this talk on the lowest part of the atmosphere, the lowest 10 kilometers, which is known as the troposphere. And in fact, we're not even going to focus on the lowest 10 kilometers. We're actually going to focus on the lowest kilometers, something called the boundary layer. And we're going to think about the chemicals that are released into this region, volatile organic compounds, and a whole load of nitrogen oxides, so NO and NO2, that are released from combustion. And the figure just really emphasises the fact that it's not just human activity that release chemicals into our atmosphere. Plants and other naturally occurring systems release a whole cocktail of chemicals into the Earth's atmosphere. And we're going to think about what happens to these chemicals now.
Okay, so volatile organic compounds, VOCs. So compounds containing carbon that turn to vapors or boil at low temperatures are all going into the atmosphere all the time. So the question is, what happens to them? Give you some examples of naturally occurring VOCs. The smell of a rose, geraniol for example, it goes into the atmosphere, and when we're smelling a nice rose, we can smell it. But where do the smells actually go to? is the atmosphere simply filling up full of VOCs with time. The smell of lavender might be another one, a smell of lemon would be a third. There are lots of VOCs, lots of volatile organic compounds into the atmosphere. Where do they go? Well, the atmosphere, of course, is full of oxygen. Oxygen is a useful reactive chemical. We've got oxygen in the layers in the top of these bottles here, because there's oxygen in the air, 21%. If we shake up the oxygen into these particular solutions, we can actually see the evidence of oxygen taking part of a chemical reaction. We've got a bit of colour change. So let's move that out of the way and let's take it forward. So volatile organic compounds, compounds that contain carbon in an oxygen atmosphere, maybe they're just burnt out of the atmosphere. That's why we're not getting a build-up of all these smells. Combustion, of course, is important. Let's give it a go. I've got here a test tube. Over here I have a volatile organic compound. It just happens to be methanol, the fuel for drag racing cars, the simplest of the organic alcohols, CH3OH. Let's pour in a carefully measured drop of that liquid. Volatile means it turns to a vapor, so let's turn it to a vapor. Let's actually shake this up. Now you've got to be careful with methanol. Methanol is highly toxic. It will go through your skin, into your blood system and cause irreversible brain damage. So I'm shaking this up without it touching my skin, and I'm shaking it up to turn some of the liquid to a vapor. Let's pour out the surplus liquid. You can only saturate the air that's in the container, and the amount that goes in there, of course, is temperature dependent. Let's dribble out the last of this liquid fuel. Now, of course, if you were doing this, or we were in a lecture theatre at this point, I'd have to put a safety screen between you and the experiment in case the plastic container explodes. Since you're behind a safety screen of your own called a television set, we don't need to do that. So what we've got in that bottle is a volatile organic compound, some methanol vapor, we've got some oxygen, we've got a fuel-air mixture. Fuel-air mixtures are explosive. Let's add some energy into the mix, which in the atmosphere could of course come from a lightning strike, it could come from, I don't know, rainforest fire as a source. We'll knock the lights out to make this easier to see. We'll add in the activation energy. And we can see that we can burn our VOC. So maybe these VOCs are burnt out of the atmosphere. Dudley, shall we show an alternative way of burning stuff? Because that one was a nice blue flame. Having a blue flame come out means it's complete combustion. We're liberating all the energy from the fuel-air mixture into heat, light and sound energy. That was a hot water bottle. That's not the only way to burn materials. We don't need oxygen gas to burn materials. We can use an oxidizer. Here I've chosen as the fuel for human bodies. Add a small amount of that to this flask, to this mat. In the second container, I've got an oxidizer. Now oxidizers, if you've not come across them yet, you can simply think of them as materials that want to give away oxygen. Fuels need oxygen to release the energy that's stored as a chemical. Now, solid-on-solid reactions are useless unless you actually mix up the materials very, very well. A bit like making cake. And we've got this on a heat-proof mat here. And in order to get this going, I need to add a few drops of concentrated sulfuric acid to act as a catalyst. A few drops, we'll just do it with one drop. And we'll have the light, we'll turn the Bunsen out as well. One of the reasons I wanted to show you this experiment is because of the aftermath. We have got some burning going on in there, but instead of complete combustion with only blue flames, you will have seen a yellow flame there, which indicates incomplete combustion because there's soot formation. You can even see some black soot on the mat there. The smoke that hopefully you caught as the lights came back up there, is simply a mixture of solid particles in the air. Smoke is not a gas. Smoke is a mixture, in this particular case, of soot particles and some vaporized and then condensed sugar. Dudley.
Well, you've seen some examples of combustion there, and there are certainly forest fires, there are certainly lightning strikes which initiate burning, and that's one way that the atmosphere can get rid of these chemicals. But actually there are a number of different ways that the atmosphere can cleanse itself. One is through rain. So some of the chemicals that are released into our atmosphere are soluble in water and they will be removed in that way. Other chemicals will literally stick to the surface of the earth in various forms and be removed. But the volatile organic compounds that Tim's talked about, the vast majority of those are not removed either by rain or by dry deposition onto surfaces, and they need to be removed in another way. And it turns out that the atmosphere uses the energy of the sun again to form something called free radicals. And in the example that we've got here, it's producing the OH radical, which is the chemical detergent. It mops up all of the chemicals, and you start off with some ozone a little bit. It absorbs energy from the sun and breaks apart to form a very reactive oxygen atom, and that collides with a water molecule to give us two OH radicals, and that is sufficient to clean the atmosphere up under normal conditions. But unfortunately, as you well know, we have a propensity to pollute the planet, and driving vehicles and other forms of combustion, we start to add chemicals into the atmosphere. And one of the chemicals I want to think about now are one of the nitrogen oxides, NO2.
Okay, so let's make some NO2. NO2, nitrogen dioxide gas, not a particularly pleasant gas. It's not often made in school laboratories because it's highly toxic. One way of making it, a simple way, is using a piece of some pieces of copper, some ground up copper piping there, and to use some nitric acid. Not dilute nitric acid, because you'll remember from lower school chemistry that dilute nitric acid, dilute mineral acids will not react with copper, silver, gold, platinum, mercury. This is concentrated nitric acid. That brown coloration that you're seeing just about to spew over the top of the beaker is NO2. In terms of its colour, it's an interesting gas to look at. In terms of its smell, it smells a little bit like chlorine, another highly toxic gas, but of course chlorine happens to be yellow-green in colour. To stop the reaction, let's apply some lower school chemistry, and we'll add in a bit of water to dilute the acid and therefore stop the reaction. Dudley, NO2.
Thank you, Tim. Well, you'll see from the figure that this is some data from Bristol, could have been anywhere in the world actually, any major city. We're looking at a weekday, happens to be 21st of January 2001, but we could have looked at more recent data. And you'll see the level of NO2 varying during the course of the day. And there's two features I want to alert you to. There's a rise and fall between around 7 o'clock in the morning through to 10 o'clock in the morning. And then there's another rise and fall from about 3 in the afternoon through to about 7 in the evening. And I know that you're already telling me that you know why that is. It's because of rush hour traffic, people coming into and out of work or school or whatever it may be. And as a result of being in a vehicle, either a bus or a car, it's releasing nitrogen dioxide into the atmosphere. Now, Tim also showed you that nitrogen dioxide is a brown gas, and that means that it will absorb sunlight and it will break apart to form NO and O, and that O atom will add to O2 to form ozone. And before you're getting confused, ozone up in the stratosphere is very good. We want to have ozone there, but ozone down at the surface, or high levels of ozone down at the surface, is bad. It's a toxic gas. It's not good for plants or for humans to breathe in if you're asthmatic, or for structures or for animals. So we don't want to have high levels, and if it does become very high, then you end up with photochemical smog, and again the figure there tells us a little bit about the photochemical smog. You end up with this brown haze over the city, which I know that you would have seen in pictures and maybe unfortunately have experienced yourself. So we have a number of gases that are being put into the atmosphere in small amounts, but actually have a very profound effect. So the other product of combustion is carbon dioxide, CO2. And we've been making measurements of CO2 here in Bristol for quite some time. And although this is some data that we've collected very locally, you'll see that the level of CO2 varies quite a bit, and that's because of the amount of traffic that's on the road. But there is also a seasonal cycle there, where it's highest in the winter and lowest in the summer, and there's a better diagram of that. If we were to go to Hawaii, as Keeling did back in the 50s, and make continuous measurements of carbon dioxide, we would see the figure that his amazing research produced. What it shows us very clearly is that Hawaii is obviously a background site far away from major land masses, and the level of CO2 has gone up over time, and there has been some oscillations backwards and forwards, seasonal cycles, where it's highest in the winter and lowest in the summer, and that is because of photosynthesis. So in the summer, the biomass, the number of plants and the leaf area is high in the northern hemisphere, and it draws down CO2, and in the winter the deciduous plants die back and the amount of CO2 absorbed is less, and so it pops back up again. So there would be an oscillation up and down over the course of a year anyway, but certainly not the continuous increase, and we know that's due to fossil fuels. Okay, we're going to now think about climate in general, not just CO2. But before we do that, I'm going to ask Tim if he can tell us a little bit about carbon dioxide.
Okay, enter stage left. Carbon dioxide. Normally at room temperature and pressure, it is a gas. Here, I have some solid carbon dioxide. Solid carbon dioxide looks like ice. It contains absolutely no water, and its nickname therefore is dry ice. This stuff is at least minus 78 degrees centigrade, and if I was to hold it in my hands for any length of time in a fixed position, I would destroy my skin cells. I would actually get frostbite. Moving it quickly from one part of my skin to the other means that I won't get that, and I don't need to get my gloves on. Dry ice is an interesting material for a number of reasons, and whilst Dudley will go on to talk about carbon dioxide gas, I just thought I'd take this opportunity to show you a little bit of the weirdness of CO2 solid. I've just put into this rubber glove here approximately 22 grams of CO2, so half a mole. CO2, of course, is 44 grams per mole. Let's take some heat energy out of my hand and put it into this glove. And what I want to demonstrate to you, hopefully if there's no hole in this glove, is that when you warm up dry ice, when you actually put some energy into the carbon dioxide crystal lattice of the solid, you don't melt it. Instead, the solid goes straight to a gas. That's an example of a sublimation. Very, very unusual in terms of the number of compounds that will do that. Dry ice actually sublimes. You might use that fact to work out why, if I take a thin layer of dry ice and a newish frying pan available from Sainsbury's and put it onto dry ice on a hard surface, this happens. Now, I'm not going to tell you why that happens. I want you to work it out for yourselves, or of course go onto the internet and look it up. Now, the important part, the very important part, is what happens with carbon dioxide and water. In a moment, once we've got a nice white background set up for you, I'm going to put some tap water into that large beaker. Tap water, of course, not pure water. I'm going to take its pH. Tap water is sweetly alkaline, so we take some universal indicator solution. pH indicator. It's the darker green indicating pH 8. Let's give that a good mix. Let's make it slightly alkaline. Let's make it strongly alkaline. We'll add a bit of sodium hydroxide, turn its pH from 8 to roughly 11 to 14. The indicator here doesn't break up the differences between pH 11 to 14. And we can see it's that nice purple colour. Watch what happens when we introduce some dry ice, some carbon dioxide to water. Now I might just wiggle this about to make it easier to see. The carbon dioxide, solid. Some of it is subliming. Now room temperature water is 102 degrees hotter than the sublimation temperature of dry ice. Some of the carbon dioxide is subliming to carbon dioxide gas, a state change, CO2 solid, CO2 gas. Some of the water vapour that exists above a water solution is condensing down to cloud. So we're getting water gas to water liquid, another state change. Both state changes are physical properties. The chemical property is happening in the beaker. You've seen the pH drop through the purple, blue, green, yellow to orange stages. It's not going to go red because the carbon dioxide that has dissolved forms carbonic acid that neutralizes the sodium hydroxide, and surplus carbon dioxide, surplus carbonic acid solution is weakly acidic. Dudley.
So we're going to focus a little bit for the rest of the talk on climate. And the simplest way to do that is actually to use a granny. We have our illustration here. Granny's sat in her chair, and Granny's very, very sensible. She's sitting in a room. She knows where the best place to sit in the room is, so she's not too hot and not too cold. She knows if she sits too close to the heater, she's going to be too hot. If she sits too far away, she's going to be too cold. So Granny finds a nice place to sit. Well, actually, it's very similar with the Earth. You imagine where the Earth is relative to the Sun, to the heater. If we do a simple physics calculation, we can work out what the surface temperature of the Earth should be based on the energy it receives from the Sun. And if you do that calculation, you end up with a predicted temperature, average temperature of about 10 degrees. Everything is great. It means that the water on the planet is mainly in a liquid form, which is what you want, and the planet becomes habitable. It's known as the Goldilocks Effect, and the Earth is deemed to be in the habitable zone in our solar system. Well, unfortunately, there's a little problem with that, in that there is not just a straightforward system. There are clouds in the sky, of course, and there are ice surfaces in the North and South Pole and in various other parts of the world. And these all act like mirrors, so this energy from the sun gets reflected back to space. And about 30% of that energy, in fact, is reflected back to space. And so Granny doesn't get as much energy as she thought she was going to get. So what does that do? Well, if you look at our Granny model, what we find is that it's like an animal or a small child coming and sitting in front of the fire. Granny thought she was nice and snug, but actually she's not getting as much heat as she thought. And if that were the sum total of the Earth's system, the average temperature of the Earth would be minus 18 degrees because of that energy loss through reflection back to space. And so the Earth should be actually snowball Earth. We should have ice everywhere, maybe a thin ring of water around the equator, but everywhere else should be freezing cold. Clearly that isn't the case, so there must be a way in which the Earth system warms itself back up. Now, there are a couple of things that Granny could do. Granny could move closer to the heater, or Granny could get rid of the animal or small child that's blocking the heat. Well, those things can't happen in the Earth system. We can't get rid of water, and we wouldn't want it. And although the distance between the Earth and the Sun varies, it's nowhere near enough to recover that heat that's been lost. So Granny could also get herself a blanket, and that's effectively what the Earth does. And if we look at this figure, what it's showing us is if we imagine we're out in space, we've got our spacesuit on, we've got infrared goggles, and we're looking at all the heat energy coming from the Earth, we would see a so-called spectrum as the one shown there. And there are big bites taken out of that spectrum. There are parts where the energy that the Earth's releasing is not escaping to space, but being absorbed by the atmosphere. And one of the gases in the atmosphere that does this is carbon dioxide. Another gas is ozone. That's pollution ozone, not the ozone up in the stratosphere. That's ozone that we're creating through pollution. There's also methane, nitrous oxide, and a variety of other gases that are so-called greenhouse gases. And these act like a blanket. They absorb the outgoing infrared radiation and direct some of it back down to the surface and give us a little bit of extra heat. And if we now look at our granny model, we have the three components. We have the heat, the sun, we have the clouds and ice, which is the animal or small child, but we also have the blankets, which are the greenhouse gases. And let's be clear, without greenhouse gases, life on the surface of the Earth would be very, very different. We need the greenhouse gases to be there, and if you add all of those components up and do a little calculation, you end up with an average surface temperature of 16 degrees. So greenhouse gases are actually very, very important. But what happens if you start to increase the level of greenhouse gases in the atmosphere? Well, we can look at this in a number of ways. We can look at tree rings, we can look at all sorts of other things, but a very effective way is actually to drill a hole in the ice in either the North or South Pole and extract an ice core. And you'll see from the figure there, and as you chop up the ice core, you're able to analyse the bubbles of gas that are there and to work out the level of greenhouse gases that have been present in the distant but also recent past. And if we look at the levels of carbon dioxide and also methane and nitrous oxide, we see that their levels were pretty constant over the last the 1,000 years from 0 AD through to around the 1800s. And then their levels started to increase, and that coincides with the start of the Industrial Revolution, where we were burning fossil fuels at an increasing rate and releasing a whole load of greenhouse gases into the atmosphere. And nitrous oxide as well through the use of fertilizers and other activities. But we see a consistent story that the greenhouse gases have been increasing. So what has this had impact has this had on the temperature? Well, if you compile some 60 million surface temperature measurements that scientists have done over the last 150 years, and assume that the first 50 years you average that out and see how temperature has changed since that time, you see that the temperature has gone up by approximately 0.75 or 3/4 of a degree. And when you run computer models of the atmosphere to reproduce that, and you first say, okay, let's just look at all the natural variability that could be there, volcanic eruptions, changes in solar variability, you find that you cannot reproduce that curve very well. If you then take all of that out and just put in the changes in greenhouse gases caused by human activity, you then start to get a better agreement, certainly in the last 30, 40, 50 years. And if you put all of those things together, you get really quite spectacular agreements. So we believe that we understand the Earth system, at least to a first degree, pretty well. And that increasing greenhouse gases will increase the surface temperature of the Earth. The question we should be asking is how quickly it will increase the surface temperature and what the surface temperature ultimately will be. How high will it go? And we may wonder what will happen if we carry on as we are, and what will happen to the weather for example, in the UK. And it's certainly expected that if you start to increase the level of greenhouse gases, you'll have more extremes of weather. We'll have wetter winters and drier, hotter summers, for example. And that may cause a number of different changes to the way we live. And of course, this will be more extreme in other parts of the world. Now, we don't want you to go away from this talk feeling doom and gloom. Is there anything we can do? Well, yes, there is. And the idea here is around these things called stabilisation wedges. If we think of the amount of carbon that we're releasing into the atmosphere, certainly in 2005 it was 7 billion tonnes and it's gone up since then. We imagine what will happen in 50 years. By 2055 we're expecting it to have doubled, and we'll end up with 14 billion tonnes of carbon being released into our atmosphere. Well, if we do that, the level of CO2 will be very high. It'll be highest it's been for 3 million years. And the impact on the climate and weather and our lifestyle will be very dramatic. We want to stop doing that. We want to stop releasing that carbon into the atmosphere. Are there ways of doing it? Well, there's no one magic bullet, there's no one way of doing it. But if we were to split that yellow triangle in the picture up into 7 and say that each one of those wedges saves us a gigaton of carbon or 1 billion tons of carbon a year, are there technologies that exist? Well, there are a number of technologies that exist. We're not going to go through all of them, but we're just going to give you a highlight of a few. Well, the first thing that we can do is to improve the fuel economy of cars. Obviously, we could go to electric cars, which would save a massive amount of carbon, but if we were to go through an interim phase and increase the efficiency of cars so they ran at 60 miles per gallon rather than 30 miles per gallon, that would save us 2 wedges of carbon straight away. The other thing that we could do is also think about the buildings and make them more efficient, either better at cooling or better at warming, and that would also save us up to half a wedge of carbon as well. An interesting one is nuclear power. Obviously we could invest more in nuclear power, but if you don't want to do that, you say, well, nuclear power is bad for various reasons and we want to get rid of nuclear power, then you've got to think about saving an extra half a wedge of clean energy. So there are pluses and minuses to these things. If you want to get rid of that, you've got to find a clean source of energy that will give you half a wedge. Another important source, and certainly is becoming even more important, is wind energy. Obviously there's certain parts of the world where this will work very well and others where it won't. But if you want an idea of how much land is required to save you a wedge of carbon, you'd need to plant a wind farm the size of Germany. And Tim has forbidden for me to make a joke about that. But we can see that actually that's not a massive amount of land that you need. And in fact, nowadays you can actually use offshore wind power, so you're not using land at all. But actually wind power could be a very important source now and in the future. But you can save a wedge of carbon by using a reasonable amount of land dedicated to wind power. Big one, of course, is solar power using photovoltaic cells, and the technology is increasing and getting better every year. But again, if you wanted to save a wedge of carbon, you'd need to have a solar farm and a solar array that was 12 times metropolitan London, or about the size of Q8. And that is actually quite a small area, of course, and you could save a wedge of carbon, one whole wedge of carbon in that way. And obviously solar power is a very important source going forward. Of course, the other thing that you can do is stop deforestation and stop removing trees. Trees, of course, are a natural sink for carbon dioxide, but you do need to plant a lot of trees in order to do that, and you'll see some figures here in the slide, but you've actually got to plant a significant amount to offset climate change. So for example, if you wanted to save a wedge of carbon, you'd need to turn the continental US into a forest. It's that kind of area that you require. So quite a massive tree planting exercise needs to take place, but it would have an impact on the climate system. And so we really want you to take away from this is that the Earth system is quite dynamic, and the impact that humans are having on it is very real. But there are so many things that we could do to offset climate change. And although we need to find 7 wedges of saving, we actually have, with technologies that exist today, over 14 ways of doing it, over 14 wedges. So we could do it twice over. So don't be despondent. There's lots of things that we can do. Now, it's always traditional in this talk for Tim to have the last word, so just like to see whether you remember something about the composition of the giant gas planets.
Okay, so over here we have some low density gases, and these low density gases I've chosen are both hydrogen. This will be a surprise to Dudley. I'm very conscious of the fact that this planet is running out of helium gas, which is needed for other purposes. We've got 2 lots of hydrogen here. Obviously hydrogen, when you burn it, is a clean burn. It only makes water, and whilst water vapour is a greenhouse gas, there's a lot of that in the planet anyway. So let's actually remind you of the combustion of hydrogen. We'll do it in the light and in the dark. And what we would like you to do is to consider why the volume of reacting gas, in other words the flame, is bigger than the volume of the balloon. So I'll take the one to my right to start with in the light. And to make it easier to see, we'll do it in the dark. At this point, on behalf of Dudley and myself, we'd like to thank you for your attention. We hope you've learned some, or reminded yourself of some chemistry. And if you've got any queries, please contact us. Thank you very much.